This is a lesson about the bipolar junction transistor and the various configurations that you can use it in. Before you have this lesson, you should already be familiar with what a bipolar junction transistor is and the basic principles of its operation. And you should be familiar with the regions of the transistor called the base, the collector, and the emitter, which I've indicated in the drawing here as B, C, and E. Now, when you're actually using a junction transistor in a circuit, there are three different ways that one can configure it. And that depends on whether or not the emitter, the collector, or the base is in common with two different parts of the circuit. Exactly which configuration one uses depends on the particular application, because all three of them have advantages and disadvantages. Okay, so we'll discuss those each one at a time, and we'll start with what's perhaps the most frequently used configuration, the common emitter configuration. In this configuration, we have two voltage sources, which we will call VBB and VCC. We also have a resistor here, which is the load resistance. Okay, so that stands or represents the device that we are powering with our transistor. And then we have R sub S, which is a source resistance. Okay. Now, in this configuration, we will have a collector current, IC, which goes this way, and we'll have a base current, which goes this way, I sub B. And of course, the whole idea of a transistor is that with a small base current and therefore a small VBB, we can control a much larger collector current. If we want to know how this behaves, then we need to look at the current voltage curve. But since this is a three-terminal device, we need an entire series of current voltage curves in order to understand how it's going to work. So what's commonly done is plot what is called a set of characteristic curves for the configuration. Okay, so if we plot VCE on this axis, okay, and VCE is the collector emitter voltage. In other words, I'm plotting the voltage drop between here, which is at the collector, and down here, which is at the emitter. Okay, so let's call that voltage VCE, the collector emitter voltage. Okay, and it's that voltage that I'm going to plot on the x-axis. This will be in volts. Okay, then on the y-axis, let's plot the collector current, which is already labeled in the diagram as I sub C. Okay, now the key is that the current voltage curve I get on this graph is going to depend on what's going on at the base. So depending on whether or not current is flowing through the base, or if there is, how much is flowing, that's going to affect the current voltage curve that I get in my graph. So as you learned when we first introduced the bipolar junction transistor, we saw that if there is no base current flowing, then both p-n junctions of the transistor are in, or at least one of them is always going to be in reverse bias, and not very much is going to happen. Okay, so if there's no base current, then we get a line down here that is basically 0. Okay, so if IB is equal to 0, then I get essentially no collector current. Okay, it's going to be pretty close to 0. But if I increase VB so that I now have a base current, what you'll find is that we get, even just for kind of a small base current. Okay, so this might be for a base current of only 10 microamps. I may get a collector current of a milliamp. Okay, so let's put a 1 there, and we'll make the y-axis unit milliamps. If I increase the base current even more, then I'll get even more collector current. So we might get something that looks like this. So at 20 microamps of base current, we may have something like 2 milliamps of collector current, and so on. Okay, that's 30 microamps. We have 3 milliamps of collector current. And you can see here we've got a current gain of about 100 if you think of this as an amplifier, since IC over IB is approximately equal to 100, then we can say that our gain, the current gain, A sub C, is about equal to 100. And notice that as long as we're above about 1 volt or so, that actually does not depend on the value of VCE. That's important later in some applications. That for the most part, if you know what the base current is, then you can predict the collector current independent of VCE. So if you're trying to get an amplifier with a stable gain, you don't want, if you don't want the voltage, like if the voltage changes from say 2 volts to 2.1 volts because of some kind of fluctuation, you don't want the gain of your amplifier to change. So notice that if I'm using, say, a base current of 20 microamps, then I'm going to get 2 milliamps of collector current regardless of whether or not VCE is fluctuating a little bit. Okay, so that's an important characteristic of an amplifier, is you want the gain to be stable, and not to depend on some kind of fluctuation that may occur in your circuit. So the common emitter set of characteristic curves shows that for the most part that's true. Now sometimes there is just a little bit of upward slope on these. If I go ahead and draw the next one for 40, sometimes they do have a little bit of upward slope. So it's not necessarily perfectly constant gain depending on VCE. Okay, I'm going to move to another page now. So if you need to pause this to finish writing something down, you should do so. But when you're ready to move on, you can unpause and we'll talk about the common collector and common base configurations. Okay, here on the left, you can see a bipolar junction transistor wired in the common collector configuration, and you can see that right here we have the two power supplies in the configuration, both connected to the collector, so hence the name. You have the load resistor and the series resistor. And then on the right is the common base configuration, okay, where we have both terminals of the power supplies connected to the base. Again, with a load resistor and a series resistor. If you need to pause to write these down, go right ahead. Okay, but as I said before, the particular configuration that you choose is going to depend on the specific circumstance. So here are the different properties of the three configurations that you might want to consider. All right, and we'll make a table. Okay, you might want to know whether or not there is power gain. Okay, by power gain, we mean, does the power in, the power out over the power in, is that greater than 1? Okay, and that would be what we're considering the input current and the output current. Is the power for one of them, for the output, greater than the power for the input? We might want to consider the voltage gain. Okay, which means that the output voltage is greater than the input voltage. We might have current gain, which I'll write as I out over I in. So do we want that greater than 1? Okay. There is the input resistance. And the output resistance, or input impedance and output impedance it's sometimes called. And then finally, whether or not the phase is inverted. Okay, so let's make a table. Here is common base. Here is common emitter. And here is common collector. Now, before I start filling in the table, I definitely want to make sure you understand that when I say the power gain is greater than 1 for the amplifier, or for that matter, any of these gains, voltage, current, or power, that we're not getting something for nothing in any case. There's always an external power supply involved. Okay. If we go back to the common emitter configuration, then we have collector current over base current equals 100. So this has a current gain of 100. Okay, but there's an external power supply here. All right, we didn't get that factor of 100 out of the vacuum. We got it from the power supply VCC. Okay, so while the transistor is enabling us to amplify the current by a factor of 100, the energy is not coming from the transistor itself. It's coming from that external power supply. Okay, so just make sure you keep that in mind when I say, that there's gain on these various configurations. There's always an external power supply involved. We're not pulling energy from nowhere, unfortunately. Okay, well, the common base configuration does have a potential power gain. So does the common emitter and common collector. So all three of them have power gain. If you want a voltage gain, the first two do have a voltage gain. The common collector does not. For current gain, the common base configuration does not. The common emitter configuration does. And the common collector configuration does. So already you can see one reason why the common emitter configuration is popular. It's because it's the only one of the three that has both a current gain and a voltage gain. Okay, but the reason that you might not want to use it exclusively is in the input and output impedance categories. Okay, for the common base, input impedance is about 30 ohms. For the common collector, it's about 3.5 kilo ohms. And for the common collector, it's 580 kilo ohms. So I should, at this point, explain what do I mean by input resistance. Well, input resistance is the amount of current that the amplifier is going to draw. In an ideal world, your amplifier doesn't pull any current at all from your source. You would like to be able to, amplify even tiny currents and not overload your source. So in general, you want the input impedance to be high so that the amplifier doesn't draw extra current. So 30 ohms, which is what the common base configuration has, is a pretty low input impedance. 3.5 kilo ohms is actually moderately high. 580 kilo ohms, that's the best that you can do with a bipolar junction transistor. So, if you have an application where the input impedance is the most important and you only want current gain, then you might use the common collector configuration, for example. Okay, now in other cases, we have a typical output resistance. We generally want that to be low because you would like the amplifier to be able to output as much current as possible. So you want its output resistance to be low. The common base configuration has a 3 mega ohm output resistance, so not very good. The common emitter configuration, 200 kilo ohms, so certainly better, but not great. And then the common collector configuration, 35 ohms. So if input and output impedance are your primary thing that you're concerned about, you would use the common collector configuration. If you need to amplify both current and voltage, then you go with the common emitter. You might be thinking, okay, why would anybody use the common base configuration since it seems to be the worst in most of the categories so far? And one of the reasons is the bottom line, the phase inverter. Okay, when you have a phase inversion, then the output voltage is proportional to the negative of the input voltage. I wrote approximately equal to. I didn't mean equal to. I meant proportional to. Okay, so if you have a positive input, you're going to get a negative output and vice versa. In some applications, that's fine. In other applications, you can't tolerate that. You need the voltage to stay the same polarity that it was when it came in. The common base configuration does not have a phase inversion. The common emitter configuration does, and a common collector configuration does. So you can see that all three of these configurations have some strong points and some weak points. None of them are outstanding in all categories, and for that reason, in extremely sensitive or demanding applications, such as microprocessors, for example, then the choice would be none of the above. We're not going to use a bipolar junction transistor. We'll use a different kind of transistor entirely. And we'll learn more about what those different kinds of transistors are in later lessons. But for this lesson, what you need to remember is that there are three configurations in which one can use a bipolar junction transistor, and that each of them have advantages and disadvantages. Also, you should be able to interpret the characteristic curve diagram, VCE versus IC, for multiple values of base current. And that ends the lesson.